an update on Zoom and I don't. Ah, I figured it out. I figured technology out. That's a shocker. So. All right, we have started the last unit. And so just a reminder, the last unit the prior unit that we just completed was linear functions. And what was the linear model of that equation? Yes. I heard it whispered. Y equals mx plus b. That means it makes a line. What's true about a linear relationship? If I asked you to prove or, yeah, what is constant? Average rate of change is constant, okay? So that was linear. So last week on Friday, then we looked at exponential functions. And in that, something is always constant. If you don't remember, it's on the bottom of page 55. Correct. So instead of a constant average rate of change, we have a constant percentage, and a percentage is a rate. So if you recall last week, we talked about the rate, which was R, which would be given to you like a 3% increase. Well, that is a constant percentage increase, okay? So that's what's different about exponential. We also looked at and learned what that equation model is. Layer, so I'll do this. And that is this equation here. So rather than y equals mx plus b, we are now looking at n equals p times a raised to the t power. All right. So what is p? That's your initial value. So in linear, it was the b. Now the p is the initial value. All right. Now that in linear, we had an average rate of change. For exponential, what do we have? Here's your hint. It's A. Slope was linear, which is average rate of change. A is a factor, and it can be either a growth or a decay factor. We talked about what is always true about the growth factor. It's always going to be a number greater than 1. What's true about the decay factor? It's a number that's always smaller than 1. Okay, so I know you didn't have an assignment due, which means you probably haven't thought 2 seconds about functions since last Friday. So I wanted to go over that first. All right, so example 3 is where we're going to pick up from. And it says find the missing values. Okay, notice we are talking about growth. So a percentage growth, this is always given to you as R, which is a rate. Your growth factor, so since we're talking about a growth factor, this is your A, and you just told me if we're talking about growth, that means my growth factor has to be a number that is larger than 1. And from the notes that we did on Friday, we know A to be 1 plus R. Now, here's 1, R is 4%. Do I take 1 plus 4% and get 5? No, what do we have to do with that rate? We convert it to its equivalent decimal. So remember, when you convert to a decimal, you move the decimal point 2 places. So 4% is the same thing as 0.04. So this first growth factor, A, is going to be 1 plus 0.04. So we know our growth factor then would be 1.04. All right, let's go ahead and do all of these that give us the percent first. So 23%, that equivalent decimal is 0.23 or just 0.23. So what would that growth factor be? 1.23. You just add it to 1. Glare for y'all. Why is that a glare? Because I don't have the light on. I don't know why it does that. All right. What is the equivalent decimal for 2.3%? 2.3 is the percent. To change a percent to its equivalent number, you have to move the decimal point 2 places. 0.023. You move the decimal point 2 places, you get 0.023. So if you don't remember how to convert a percent to a decimal or a decimal to a percent, you may need to Google that and refresh your memory or get some practice on that, because we're going to do it a lot in this unit. Okay, so if I add 1 to this, I get 1.023. And each one of these is a number larger than 1, so we know it represents growth. Okay, now what we're going to do is do that kind of backwards, right? So we know that A is 1.12. So we want to ask ourselves 1 plus what gives us 1.12? What would you add to 1 to get this number? 0.12. So we know then my rate as a decimal is 0.12, but I'm going to rewrite that. Sorry, I'm trying to get it out of the glare. I don't know why it's doing it. Let me see if the lens is good. What do you know? The lens is dirty. Okay, I thought it was lighting. So we move the decimal point now 2 places to the right, and this would give us 12%. All right, so we know the growth factor is 1.07. So again, 1 plus what is 1.07, which is 0.07. Move your decimal 2 places to the right, and it's 7%. And the easiest way is just to go, oh, if I take away 1, I'm left with 0.12 or 0.07. You can just do it quickly that way. Okay. All right. Suppose that because of disease, the population of a mythical medieval land decreased by a rate of 3% each year. The initial size before the disease struck of this medieval population was 250,000. Okay, now the first thing I don't want you to lose sight of is we're still dealing with functions and variables. And so this doesn't ask it, but we're going to go ahead and define that. Suppose that because of disease, the population of a mythical medieval land. Oh, wait, no, this isn't the one. Oh, never. Yeah, we can do this. Okay, the population of a mythical medieval land decreased by a rate of 3% each year. The initial size before the disease struck of this population was 250,000. Okay, so in this, we are talking about decrease right here. So our function is going to be the population, right? Okay, so we know that we have a decrease, and we know that it is a rate of 3%. So this rate of 3%, we know they are giving us R. And that could be rewritten as 0.03. Now, because they tell us it decreased, then we know that we have a decay factor. Okay, all right, the initial size before the disease struck was this amount right here. Okay, so part A, what's the initial value? That's 250,000. Okay, in our exponential equation model, what letter is used for initial value? P. So we have just found P is 250,000. And now it wants the decay factor. Okay, so when I see decay factor, I think, okay, I know my decay factor is A, and because it's decay, we're going to do 1 minus R. Well, we just talked about that R is 0.03. So we're going to do 1 minus 0.03. So A is 0.97. And that is a number that is less than 1. So I know I'm doing good. Okay. Then in part B, now it's wanting you to write an exponential function. Oh, here's where it was at. For the population of the medieval land as a function of the number of years after the disease struck. So if I asked you to write the function, what letter in the exponential model do we use for the function? N. And so N is the population of the medieval land. So I'm just going to write population or pop of medieval land. And the variable is, what letter is used in the model? T. And this would be years after struck. Now, it did not ask for this. I'm going to do it for this example and the next example, just to remember we're still dealing with functions and variables. All right, so it wants us to write an exponential function. So we're going to use the model N equals P times A raised to the T power. So N is my function, so I leave it as N. P we found in part A is 250,000. A is your decay factor, which is 0.97, and we raise that to the variable T. So that would be the exponential equation model for this particular problem. All right. The population of a small Oklahoma town is decreasing by 1% each year. So decreasing 1% each year. All right, so we know that they give us R equals 1%, and we know we have decay because of the word decreasing. The population of the town was 2,548 in the year 2000. Okay, just as a good reminder, the function here, we're going to use N. What do you believe the function to be in this problem? I'm just going to do population of town just for abbreviation's sake, but it is the Oklahoma town. All right, what is your variable? I'm going to call it T, but how would I write that?
Years.
And that's what I want to remind you. This is an example. We do have years, but this is since 2000. So be careful of that. Okay. Now, this first question asks, explain why the population of the town can be modeled as an exponential function. All right, when we explained if it could be a linear, we would say that the function, the function's average rate of change is constant. Okay, that's not true for exponential, but what is constant for exponential? The percentage, and in this case, it's a percentage decrease, okay? So we would say the function or the population of the town, so the function has a constant percentage, and in this case, it's a decrease of 1% each, whoops, not period, each year, period. So the key here is that it has a constant percentage decrease. That's what makes it exponential. And then part B wants us to express this information as an exponential function. So it's asking for the equation. Okay, all right. So when I look at this, I go, okay, I need two pieces in order to write the equation. I need to know or find the initial value. And I need to know or find, in this case, it was a decay factor. Okay, so let's start with the initial value. Was that given or can I find the initial value? Okay, initial value is not ever going to be a percent. Percent's always going to be a rate that goes with the decay or growth factor. So that percent we'll deal with it with the decay factor.
2,548.
Yeah, they tell us the population, the year 2000, that's where we're starting, and that population is 2,548. So my initial value is my initial population of 2,548. And then our decay factor A, since it's decay, we know we'll do 1 minus R. We know R is 1%, which is also written as 0.01. So our decay factor will be 1 minus 0.01, which is 0.99. So now I have all the pieces that I can use my exponential model. That model says your function, we're calling n, is equal to your initial value, which is 2,548, times your decay factor, 0.99, raised to the variable t. So this would be the equation model that we would use. Now the next page is part C and D of this same problem. So I am going to write the equation that we found at the top of the next page. All right. If I were to write my information in an ordered pair, what would that ordered pair be?
And, 5.
I don't want numbers, I want letters.
Okay, factor the initial value.
An ordered pair is always an X, Y, X represents Y. And X and T represent the variable. So remember, the first one is always the variable, which in our calculator is X, but our variable for this is T. Y is always your function in your calculator, and for us, we define the function as n. So the ordered pair does not include the rate and the initial value. You use those in the equation, but not in the ordered pair. And T, if you remember, was years since 2000, and N is your population. Okay, so In part C, what is the population of the town in the year 2005? And this is, you were working ahead, so you were giving me information on this, and you were correct. Now, what is given, function or variable value? Okay, look at year, years goes with variable, so we're given the variable value. So my question is, does T equal 2005?
Equals 5.
It is 5, because we know it's since 2000, so we have to subtract the year 2000, so we know it's 5 years. So T equals 5. Okay, so how would I put that in functional notation in relationship to my exponential equation? That's exactly right. So n at 5, 2,548 times 0.99 raised to the 5th power. So we're finding the population 5 years after 2000 is, and it's whatever we calculate. Now we do know, what do we have? Growth or decay here? Decay, so doesn't it make sense? It better be a number smaller than my initial population? Yeah. All right, so reminder how to put in your calculator, 2,548, open parentheses, 0.99, close parentheses, and then this up arrow is how you get to the exponent of 5. I'm gonna go out 2 decimal places, pay attention to WebAssign. I don't know what they will have you do. So we have 2,423.12 what?
Population.
Yeah, so I'll say people, it's population. And then I asked myself, does my answer make sense? And I do have a smaller number, and this was a decay problem. If I would have calculated 5,423, that wouldn't have made sense, because that would represent growth. All right, part D. How long will it take the population of the town to decrease to half the size it was in the year 2000? Okay, so we're talking about population. Is population function or variable? Function. Okay, so we're quote unquote given the function variable. They don't give us the number outright. But we know we are talking about the function variable, and right now that is initially at 2,548 people. And we want how much of this? Half of this. So you can divide it by 2, or you can multiply it times 1/2. How many people do we have? Okay, so we are given the function value. All right, so when I take a look at my exponential equation, this is n. So in place of n, I'm gonna put 1,274 equals 0.99 raised to the, nope, I left out half the equation, sorry. 1,274 equals 2,548 times 0.99 raised to the t. Okay. Now, in the last unit, when we did problems like this, it was linear and we just solved for the variable. But now that variable or the unknown is up in the exponent, it is not as easy to solve. So if you were in algebra for STEM, you would learn how to solve for that unknown by normal algebraic steps. We're not going to do that in here. So where do we go to if we're not going to solve it algebraically? What do we use? The calculator. Okay, so I know I need to use the calculator.
So I'm gonna remind us, I'm gonna put in here, we're gonna use the calculator.
All right, how am I gonna do that on my calculator?
Correct. So we're gonna enter this as Y1, and we're gonna enter this as Y2. Now, on your calculator, when you go to Y equals, because I had a class at 9:30, I turned my plot off. If it's on, it may not, if you don't have any lists entered, it won't affect it. If you do have lists entered, it will. And for some, it affects it. So if you want to turn, so if yours looks like this, that means your plot is on. So you can go up to it, hit enter, and you can turn the plot off, so it won't mess with this. Okay, so we're gonna enter Y1, which is 2,548, open parentheses, 0.99, and we're gonna raise that, that's that up arrow, and we don't have a T, what do we use? X. Then we're gonna go to Y2 and put in 1,274. Okay, so the first thing that we did is we entered Y1 equation and Y2. All right, so now where do I go? Not yet. We have to do one more thing first. Okay, so we would always go to window first. Now, when we first learned this, it would always tell us the window to use, wouldn't it? I don't know what your numbers are at. They might be fine. Here's where my numbers are at. I'm gonna leave them alone because I really don't know what number to use. But ultimately, when I now do zoom 0, what do I want to happen with my two lines? I want them to intersect. So if I do zoom 0 and my lines don't intersect, then what I'm gonna do is go back and change my window. Okay, so mine started and it did this one. And then it did this one, and I see no intersection, right? Okay, so I'm gonna go back to window. And it looks, so notice my X maximum is at 10, which means this horizontal axis only goes out to 10, and it looked like it was way over here. So I'm gonna change that to 100. And then I'm gonna do zoom 0 again and keep my fingers crossed that they intersect. Okay, that's looking better. And sure enough, they're gonna intersect. So now I know I can find that intersection. Does anybody remember what we go to next? It's second trace, which is calc. And what number? So second trace, which technically is calc, and then it is 5 where they intersect. And then this is where we go enter, because it's first curve, enter, second curve, enter, guess, enter, and then we get intersection. Now, this is the answer you're going to get. And I noticed some students didn't quite grasp this. I'm going to go 2 decimals. 68 point, is that 97? And Y would be 1,274. Okay, so remember in your calculator, X is the variable, Y is the function. So for our equation model, our variable is T. And our function variable is N. And if I label them, this would be 68.97 years, and this would be 1,274 people. Okay, now, which one did it ask for? T. It asked for T. How long would be years? So the answer to this question is T equals 68.97 years. Now, what if I asked you, and I'm running out of room, so I'm gonna hold it, I'm gonna turn it this way. What if I said, or I asked you, what year is that? Two thousand what? And I would probably round to 69. So I would be since 2000, and I would add 69 years, so 2069. Depending on what WebAssign said, it would either be 2068 or 2069. Because it happened during 2068, but almost when the year was over. So I don't know which way WebAssign's gonna ask that, but you need to be able to answer it either way, okay? All right, so we've been talking about decay, and we know that decay means that our factor is less than 1. Again, percentage decay, this is your rate. And your decay factor is A, and for decay, that's 1 minus R. Okay, so let's start with the ones where they have 4%. So we know 4%, move your decimal 2 places to the left, that is 0.04. 23% would be 0.23, and 2.3% is the same thing as 0.023. Always move your decimal point 2 places to the left. Okay, so my decay factor A is 1 minus R. So you're gonna do 1 minus 0.04. This would be 0.04, and what is that gonna leave you with? 0.96. So for the next one, it would be 1 minus 0.23, which would give us what? Mhm. All right, and then the last one would be 1 minus 0.023. What does that give us? 977. Now, the one where students sometimes have a little bit of problem is when they're given the factor and then they have to tell me what is R, okay? So we know that our decay factor is 0.88. So we want to ask ourselves, 1 minus what gives us that 0.88? 0.12. So this is 0.12. And then when we convert that to a percent, move the decimal point 2 places to the right, we get 12%. All right, think of 0.88 as 88%, because that's what 0.88 is, right? Okay, what is 88% plus 12%? 100%. So these two columns, if you think of both of them, if it's easier for you, if it's not, don't worry about it. But if I go, 88%, what plus 88% is 100? It's 12, and then double check, 12% plus 88% has to be 100%. Same thing here, 0.04, that's like 4% and 96%. Those add up to 100%. 23% and 77% add up to 100%. Okay. All right, so then the next one, again, we're asking ourselves 1 minus what is 0.93? Be careful, 0.07, which would be 7%. That's where you do have to be careful, because 0.7 would actually be 70%. That's not what we have, okay? All right. fill in this table. I'm gonna give you just a minute or ish to fill that table in on your own.
Okay, any idea why I highlighted orange and green?
One thing.
Exactly. So if you'll notice the top one, it's one, it says growth, and then over here, both of these numbers are greater than one. So I know these three deal with growth. Here it says the word decay, and then these two numbers are less than one. So I know these are examples of decay. All right, so 20% is equivalent to 0.20. So that growth factor is 1 plus 0.20 or 1.20. Now, when you're given the factor and you have to give me the percent, just basically eliminate that 1 and see what you're left with. So we're left with 0.023 on this one, and we're left with 0.23 on this one. And then we just convert those to their equivalent percent, which means move the decimal point 2 places to the right. So this would be 2.3%, and this would be 23%. Any questions on the growth part, going back and forth? I think that's typically the easier of the two for students. Okay, now we have decay. 19% is the same thing as 0.19. And on decay, we know we subtract from 1 because our number needs to be a number smaller than 1. Did you get 0.81? And 19% plus 81% is 100%. So I know I'm okay. All right, so then on the next one, we know that 1 minus something gives us 0.82, and I need to find out this number. The easiest thing is just to do 1 minus 0.82, and then you're left with what you're looking for. What'd you get? 0.18. Which is 18%. And 18% plus 82% is 100%. So then the last one, 1 minus what? Is 0.15. This is a big decay. So ask yourself, 100%, 15% plus what percent is 100%? 85%. So it would be 0.85 or 85%. That's a big decay. Really, really fast. I would hope that would not be an investment because I would be really, really sad. So you'll need to be able to go back and forth with those. So if that's something you struggle with and you want to ask me more questions after class, please feel free to do so. Okay. So then the second question, you initially invest $500 in a savings account that pays a yearly interest rate of 4%. All right, so in our, first off, we know this is an exponential model because we have a constant what, increase or decrease percentage? Increase. We have a constant percentage increase of 4%. So that's what makes it exponential. What is the $500? That's our initial value, and what do we label that as in our model? P. So we know that P is equal to $500. And what is the 4% labeled as? Not A, R. And that's what you have to be careful of. Now, it will help us find A. I do agree with you on that. Okay, write a formula. So we're gonna write a formula so we know we need our initial value, which you already told me is P equals 500. And we know we need our growth factor, which is A, and that is found by 1 plus what? And what number will I use? 0.04. So 1 plus 0.04, so we get 1.04. So now we can write our equation in, that's my savings account balance, right? Equals my initial value, 500, times my growth rate, 1.04, raised to the what? T. The bigger this number is, faster my money grows. That's a pretty small growth rate, but it's better than a decay. All right, how much money will be in the account after 5 years? What is given? Both are correct. The variable value, and I heard somebody say T, and that's what our variable value is. And it's not cents a day, so we just use 5. So N at 5 years is equal to $500 times 1.04 raised to the 5th power. Now, we're finding what? How much money's in there? That should tell you how many decimal places to go if we're talking about money. 2. Horns down because we're not Texas fans. I'll take it as a 2, but it's also horns down. My household is Sooner fans. So, all right, has anybody got that calculated?
608.
All right. That's all it asked for, so I'd be done. But let me ask you, if I was looking at this and said, okay, how much money did I earn in interest? $108.33, right? Because the $500 is mine. So it didn't earn a ton in 5 years, but again, we didn't invest a lot. And again, I didn't have to pick up anybody's trash or wash a toilet to earn that. It just sat there and I made that money, which is always a good thing. Okay, last question. How long will it take for the account to reach $1,000? So what were we given? That is correct, which is our function value. And we're given N equals $1,000. So when I'm looking at my equation in place of n is where I put 1,000. So that'll equal 500 times 1.04 raised to the t. And then just like we did prior, we're gonna do y1 and y2. All right, so I'm gonna clear these out. Raised to the x. Now I'm gonna hit window, I'm gonna leave it alone, and then go to zoom 0, and if that isn't helpful, then I'll adjust it. All right, there's one. Okay, it looked like it's doing it down here, which I don't love, so I'm gonna go back to window, and I'm gonna do, instead of 100, I'm gonna do 25. And sometimes it's just a matter of throwing some numbers in there until it is pleasant. There we go. Go back to zoom? No, I'm sorry, window. Do 0 as your min and 25 as your max. And then you went to zoom 0? Okay, I'll take a look at it here in a second and see, but we're running out of time, so I'm gonna go ahead and finish this. So then we go second trace, which is calc 5. First curve enter, second curve enter, guess enter. And so we get x equals 17.67, and I get y equals 1,000. So we know our variable is t, so this is 17.67 what? Years. And then we know this is n, which is $1,000, and which one did it ask for? So that's how long it'll take that $500 to become $1,000. Okay. I'll have stop share on this. Different than the prior. There we go. Okay, I figured it out.